In this video, we're going to go over how to represent graphs, and we're going to focus on adjacency lists. So first, let's review graphs. We're going to be using this graph in a couple different examples of just a graph that connects airports, and a couple things to go over. We know that it's not too bad to keep track of a set of nodes, right? We could use a vector, a set, a list. There's so many different options. The tricky part is how do we keep track of how edges are connected in a graph? So we know that we need to keep track of every vertice, which is kind of made up of the starting point, the ending point, and the weight. So this particular edge is going to keep track of this edge that's drawn in the graph. Couple things to point out. Edges can be directed or undirected, and that might affect how you might want to represent your graph. Weights could be present or absent. It's not required that graphs have weights. Sometimes they might, all edges might have the same weight, which means that you might just have no weights at all. Multiple edges are allowed, so you could have multiple edges between O'Hare and Dallas-Fort Worth. Here we have one, but you could have another one that has a different weight. That would be allowed. Cyclic edges are allowed, and here's an example of one here. Dallas-Fort Worth has a edge that comes back to itself, and that could come up in all sorts of different applications. For this particular one, maybe there's a helicopter ride that leaves Fort Worth and comes back, but you could just imagine that there's any round trip ride that returns back before it stops anywhere else. And what we're going to do is now talk about, well, how do we actually do this? A list like this is not a good way to do it. It's not an efficient way at all. And so what are some of our options? So there's really two different representations that we can think of. When we talk about these representations, we're not talking about data structures or abstractions. We're just talking about ideas. So don't get yourself married to the idea that any of these concepts are a particular data structure or a particular abstraction that needs to be used. There might be various ways to do that. Now, the adjacency matrix is the most straightforward one. So basically, you just set up an n by n matrix where n is the number of nodes, and on one edge of the matrix you have all of the to's, and on the other side of the matrix you have all of the froms. And basically, if we want to go from New York City to O'Hare, and we have a weight of 75, so if we want to represent this edge, we're coming from New York City, we're going to O'Hare, and so in that cell of the matrix we could represent the weight. If you don't have a edge, like for example from New York City to Dallas-Fort Worth, so from New York City to Dallas-Fort Worth, there is no edge. You could represent it with some number or flag or something to indicate that there isn't an edge. So that's one idea, is a full matrix that just has all possibilities. Another idea is called an adjacency list, which is what we're going to focus on in this particular video. An adjacency list is where you have a list of the nodes, and off of that list you connect all of the other nodes that it connects to. So we know that from O'Hare we can get to New York City in 150 and Dallas-Fort Worth in 40. So from O'Hare we can go here or we can go here, right? So those are the two edges that are connected from O'Hare. And so you can represent it in something called an adjacency list. Now, I want to emphasize that an adjacency list in particular, but also an adjacency matrix, is not itself a data structure or an abstraction, but there's actually lots of different ways that you can implement these types of representations. So for an adjacency list, all it means is that we have a bunch of nodes that are connected to each other with a bunch of edges, and we basically have a table all the nodes and they are adjacent to this list of other nodes. Now, how we actually implement that, here's one idea. What if we had a map that connected the node, which would be the key, to a vector of nodes, which are all of the nodes that it's adjacent to. The node, the nodes themselves or other parts of the abstraction would also need to keep track of possible weights or something like that, but this idea that you have basically a map that's used as the actual implementation of the adjacency list representation is what I'm trying to get you to think about. But a map wouldn't be the only way to do it. There are so many different ways to do it. Maybe you use a map that maps strings to vectors of strings. Maybe you use a hash map that maps strings to maybe a hash set. Maybe you have a map that maps strings to a set. Or maybe this representation is just a vector of vectors, right? So you have a vector of vectors. You know, doesn't need to be a matrix, it's just a vector of vectors, right? There's so many different ways to do it. This idea that you have some sort of mapping that is associating each node with its outgoing edges is the real idea of the adjacency list. It could also just be kind of what's visualized here, which is like a vector or an array of a linked structure. That would also be a possibility. So that's the whole point of the adjacency list that I wanted to leave you with for this video. And that's it.